Okay, get ready to dive deep into something pretty wild today.
Yeah.
We're going to check where quantum mechanics and random numbers meet.
All right.
We've got this fascinating article from Jürgen Schneeppert.
Yeah.
It's titled Quantenzufalls-allen Generatoren, QRNGs. Sicher und zufällig.
Okay.
It's about these incredible devices called quantum random number generators, or QRNGs for short.
It is a mouthful, the
Yes.
title.
Yeah.
But really fascinating stuff.
Yeah, definitely.
QRNGs harness the unpredictability inherent in the quantum world.
Right.
It's not just generating numbers, it's producing true randomness.
Yeah, and that's really what stood out to me from Schneeppert's article.
Yeah.
You know, we tend to think of computers as masters of randomness.
Mm-hmm.
Games, simulations, and all sorts of things need random numbers, right?
Uh-huh.
But as Schneeppert points out, even the most advanced algorithms can only generate what's called pseudorandomness.
Exactly. Pseudo-random numbers might seem random on the surface.
Right.
But they're ultimately derived from a deterministic process. So if you know the algorithm and the starting point,
Yeah.
you can predict the whole sequence.
So it's like a magic trick.
Yes, exactly.
It's impressive at first, but once you know how it's done, the illusion fades.
Precisely.
Okay, that makes sense.
Yeah.
But before we go too far down the quantum rabbit hole, let's back up for a second.
Okay.
Why are we so focused on random numbers anyway?
Well,
I mean, aside from winning at dice, where else do they matter?
randomness is more fundamental than you might think.
Okay.
It underpins so many different fields.
Like what?
Well, cryptography, for instance,
Okay.
securely transmitting information online, protecting sensitive data.
Right.
It all comes down to generating encryption keys that are basically impossible to guess.
So the more truly random those keys are, the safer our data is.
Exactly.
So I guess a predictable pattern would be like a hacker's dream,
Yes.
while true randomness would be the ultimate lock.
Exactly. And it's not just security. Schneeppert also emphasizes that random numbers are crucial for making simulations accurate.
Simulations.
Right.
Interesting.
It doesn't matter if we're modeling financial markets, predicting the weather, or even designing safer airplanes. Simulations need a ton of high-quality random numbers to reflect the inherent uncertainty we see in the real world.
So we're basically injecting a bit of chaos into the virtual world to make it a more accurate reflection of our own unpredictable reality.
Exactly. And for centuries, we've depended on less-than-perfect methods to achieve this.
What do you mean?
Well, think about something as simple as flipping a coin.
Okay.
It can still have subtle biases, based on how you flip it. The coin's weight distribution, even the air currents around it.
I never thought about that.
Schneeppert even mentions how dice, with their tiny imperfections,
Oh, right.
aren't perfectly random either.
So even those methods we consider random in our everyday lives have these hidden layers of predictability.
Precisely. And when we go digital, computer-generated pseudo-random numbers, while undeniably useful,
Yeah.
they are fundamentally limited by their algorithms.
So that's where quantum mechanics comes in,
Yes.
offering us this glimpse into a world where randomness is just built into the fabric of reality.
Exactly.
Okay, now we're stepping into quantum mechanics territory. I have to admit, it can be a bit mind-bending.
It can be.
Schneeppert article gets pretty deep into the physics.
Yeah.
What are the key ideas we need to grasp to really get how these QRNGs work?
Well, it all begins with the idea that at the quantum level, things aren't so clear-cut.
Okay.
One of the most mind-boggling concepts is this thing called superposition,
Superposition.
where a particle can actually exist in multiple states at the same time.
So it's like it's in two places at once.
Yeah, that's the crazy thing about it.
Wow.
And the choice of which path it takes is completely random,
Uh-huh.
governed only by the laws of quantum mechanics.
So it's almost like the universe is flipping a coin for us.
Yeah.
But the coin is this tiny little particle of light.
Yeah, it's a pretty wild concept.
It is.
That's for sure.
Okay, I think I'm starting to see where the random in quantum random number generators comes from.
Good.
But Schneeppert also mentions this thing called Heisenberg's uncertainty principle.
Right.
And isn't that about not being able to know both a particle's position and momentum at the same time?
Yes. And that uncertainty isn't because of limitations in our tools.
Okay.
It's actually a fundamental property of the quantum world.
So we just can't know both with complete accuracy.
It's impossible.
Yeah.
And QRNGs, especially the ones based on photon detection, really utilize this fundamental uncertainty.
So it's like nature is rolling a die, But we can't even theoretically predict the outcome.
Yeah, that's a good way to think about it.
Okay, so we've got our source of quantum randomness, the photon hitting the beam splitter.
Mm-hmm.
But how do we actually build a QRNG? What does the whole setup look like?
So a typical QRNG, as Schneepat describes it, has a few key parts. First, you need a source of quantum events.
Okay.
Like a laser emitting photons or something that manipulates electron spins.
Got it.
Then you've got these super sensitive detectors.
What do they do?
They register the outcome of the quantum event.
Okay.
You can think of them like really fast cameras capturing which way the photon went.
Okay, so we've got the laser firing photons, the beam splitter creating the quantum coin flip, and the detectors picking up the results.
That's right.
But Schneepat also mentioned something called post-processing.
Mm-hmm.
What's that all about?
That's a very important step.
Okay.
The quantum events are truly random.
Right.
But there can be biases or imperfections in the physical components of the QRNG.
Ah, I see.
Post-processing uses algorithms to basically smooth out those imperfections.
Okay.
Making sure that the final output is as random as possible.
So you're taking this already valuable thing.
Right.
And refining it to make it even better.
Exactly. It's like polishing a raw diamond.
I like that analogy.
Yeah.
It seems like that's really what gives QRNGs an advantage. Harnessing quantum randomness and then fine-tuning it.
Mm.
It's a level of security we can't get with traditional methods, right?
Absolutely.
And that's probably why QRNGs are making such a splash in fields like cryptography.
Exactly.
Where true randomness is paramount.
Yes. Schneepat actually highlights how revolutionary QRNGs could be for something called quantum key distribution.
Quantum key distribution.
Or QKD for short.
Okay.
It sounds like something out of a spy movie.
It does.
But it's a real technology that has the potential to totally change how we keep our digital world secure.
You've definitely piqued my curiosity now.
Good.
I think we need to explore QKD and these other applications of QRNGs in more detail.
Yes, let's do that.
It's clear they're more than just a scientific curiosity.
Yeah.
They're about to have a significant impact on our lives.
I think so too.
In some pretty major ways.
Definitely.
All right, QKD, quantum key distribution.
Mm-hmm.
It does sound like something straight out of a sci-fi movie.
Yeah, it does.
But based on what I'm reading in Schneepat's article,
okay,
it's a real technology with actual real-world implications.
Yes, it is.
Can you break it down for us a little bit?
Sure. QKD uses the principles of quantum mechanics to create this really secure way to share encryption keys.
Okay.
And what's really cool is that any attempt to, eavesdrop on the key exchange would actually leave detectable traces.
Because of how quantum mechanics works.
Exactly.
So if someone tries to snoop on the key exchange, they trip an alarm.
Pretty much, yeah.
They can't get the information without revealing themselves.
Exactly.
So it's like trying to open a letter without breaking the seal.
Yes. That's a great analogy.
It's impossible to do without getting caught.
Yeah, and that's where QRNGs come in.
Okay.
They generate keys in a way that ensures they're truly random.
Right.
So they're uncrackable even with today's most powerful computers.
Schneepat specifically mentions this thing called the BB84 protocol as an example of how QRNGs are being used in QKD. I gotta admit, that part kind of went over my head.
Okay, no problem.
Can you explain that a little?
Sure.
Just like in simpler terms.
So the BB84 protocol is named after its inventors.
Okay.
It's actually one of the earliest and most well-known quantum key distribution schemes.
Yeah.
It uses the polarization of photons to encode the key information.
Polarization.
Yeah, imagine them like little arrows of light vibrating in different directions.
Okay.
And when you measure the polarization of a photon, you change its state.
So it's like a secret code written in disappearing ink.
Yes, exactly.
Any attempt to read it destroys the message.
Right.
And in this case, the QRNGs are providing the ink.
Yes. They ensure the photon's polarization is truly random.
So the key is unpredictable and basically unhackable.
Exactly.
And what's even crazier is that QKD isn't just a theoretical concept.
Right.
Schneepat highlights how it's already being used in the real world. Really?
Yeah, like governments and financial institutions.
Wow.
Even research networks are using it to secure sensitive communications.
So quantum-secured communications are happening right now.
They are.
It's mind-blowing to think that this branch of physics that was once considered so out there is now being used to protect our most sensitive information.
I know, right?
But Schneepat doesn't just stop there.
No, he doesn't.
He also gets into how QRNGs are revolutionizing the world of simulations.
Yes, and it's a very important application.
Okay, so simulations.
Yeah.
They try to imitate these real-world scenarios with all their complexities and uncertainties.
That's right.
But how do random numbers even factor into this?
For those simulations to be accurate and reliable, they need huge amounts of high-quality random numbers.
Okay.
Imagine you're trying to simulate something like the stock market.
Right.
You have to account for all these different variables and probability.
There are no moving parts.
And they all have an element of randomness.
Okay.
Using true random numbers makes sure the simulation really captures how unpredictable the real stock market is.
So we're adding randomness to make the simulation more accurate. That seems kind of counterintuitive.
I know.
It's like adding chaos to make things more precise.
It might seem that way, but it's crucial. Using QRNGs to bring in true randomness.
Okay.
We get rid of biases and artifacts.
Which you might find in simulations using those pseudo-random number generators.
Exactly.
Okay, so that makes sense.
And that ultimately leads to more accurate results.
Which then leads to better decision-making.
Right.
Whether it's developing new drugs or figuring out how to tackle climate change.
Exactly.
Schneppet talks about some really interesting examples.
Yeah.
Like in particle physics and materials science,
Mm-hmm.
where QRNGs are helping scientists to do more robust and reliable experiments.
Yeah, and as we improve our ability to model these really complicated systems, the implications for fields like drug discovery and environmental science are huge.
It's pretty remarkable.
Yeah.
And it sounds like the applications go way beyond just scientific research.
Oh, absolutely.
Schneppet points out that industries like finance and engineering rely heavily on simulations for a lot of things.
Right, from designing safer airplanes to creating more efficient power grids.
And the impact of QRNGs in those areas could be immense.
Yeah, it could.
Okay, so QRNGs are shaking things up in cryptography and simulations.
Uh-huh.
But Schneppet also mentions some other cool applications.
Like what?
Like in gaming, for example.
Oh, yeah.
I never would have thought about randomness being so important in video games.
Yeah, it might not seem obvious.
But it's super important for creating fair and engaging gaming experiences.
Sure.
Can you imagine playing a game where the dice rolls or card shuffles were predictable?
Oh, that would be terrible.
It would totally ruin the fun.
Exactly.
And that's where QRNGs step in.
Mm-hmm.
They guarantee true randomness.
Yes.
Which makes sure everything is fair for every player.
Exactly. Every dice roll, every card dealt.
Yeah.
Every encounter is completely unpredictable.
And that's not just about fairness either.
Right.
It's also crucial for protecting our digital stuff.
Mm-hmm.
Which brings us to blockchain.
Blockchain.
Schneppet seems really interested in how QRNGs and blockchain are coming together.
Yeah, it's a fascinating area.
I get the basics of blockchain and cryptocurrencies.
Okay.
But I'm not sure how QRNGs fit into the picture.
Well, blockchain depends heavily on cryptography and consensus mechanisms.
Right.
Both of which need randomness.
So it's all connected.
For example, in proof-of-stake systems.
Which are used to verify transactions on a blockchain.
Yes, nodes are randomly chosen to suggest and check blocks.
And this random selection is really important.
It prevents manipulation and ensures that the entire blockchain is trustworthy.
So QRNGs can guarantee that the selection process is truly random.
Exactly.
Making cryptocurrencies safer.
Yes. Schneppet emphasizes how QRNGs can generate these random selections in a way that's resistant to manipulation.
So no single entity can control the blockchain.
That's right.
It's like having a tamper-proof lottery system that's decentralized and fair for everyone.
A good way to put it.
It's really interesting to see how this idea of quantum randomness is working its way into this new financial world.
It is.
And Schneppet suggests that QRNGs could do even more in blockchain.
Yeah, beyond just security.
Like what?
Well, QRNGs can be used to build more robust and efficient consensus mechanisms.
Okay.
Which could potentially speed up transaction speeds. And even reduce energy consumption.
Wow, that's a lot of potential.
Yeah, blockchain is ripe for innovation.
And QRNGs seem poised to play a big role.
Definitely.
It's amazing how QRNGs, which came from this wild world of quantum mechanics, are now influencing everything from secure communication to gaming and even the future of finance.
It's pretty incredible.
What does the future hold for this technology?
Yeah, let's talk about that.
So QRNGs are already having an impact.
Definitely.
But Schneppet doesn't stop there.
Yeah.
He goes on to describe this amazing future. But quantum randomness isn't just some niche thing. It's a core part of how we live our digital lives.
I think he's right. It's a future that's coming at us pretty fast.
It seems that way.
Schneppet talks about some trends that are pushing QRNGs into the mainstream.
Like what?
Well, one of the most exciting is how they're being integrated with quantum computers.
Right. It's like QRNGs are becoming an essential part of the quantum revolution.
Exactly.
But why are they so important for quantum computing?
Remember how we talked about how quantum mechanics is inherently probabilistic?
Yeah.
Well, quantum computers actually use those principles.
Like?
Superposition, entanglement.
Right, the whole deal.
Yeah, to do calculations that classical computers just can't handle.
Wow.
But a lot of these quantum algorithms need a source of true randomness to work, right?
So QRNGs are like the secret ingredient, the random seed that lets these quantum algorithms do their thing.
That's a great way to put it, and Schneppat says it's not just algorithms either.
What else?
Well, QRNGs can also make quantum computers more stable.
Okay.
And they can even improve error correction capabilities, which is important.
Right, because quantum computers are super sensitive to noise and errors.
Yeah, they are.
So it's like building quantum level security into the very heart of the technology.
Exactly.
It sounds like QRNGs are the unsung heroes of quantum computing.
I'd agree with that.
They're quietly making sure that these incredibly powerful machines actually work.
And work securely.
Right, reliably and securely.
Yeah.
Schneppat also mentions these things called quantum communication networks.
Yes.
I'm having a hard time even picturing what that would look like.
It's a pretty complex concept.
It is, but it sounds like QRNGs will be essential there too.
Definitely. Quantum communication networks are all about creating these ultra-secure communication channels using quantum mechanics.
Okay.
And just like we saw with QKD, QRNGs are key for generating the unbreakable keys that secure those channels.
So they're protecting the information as it's being transmitted.
Yes. And Schneppat even suggests the possibility of these global quantum communication networks.
Global.
Yeah. Powered by the randomness of quantum events. It's pretty mind-blowing communication that's inherently secure at the most basic level.
It sounds like something out of science fiction.
It does.
But it's amazing to think it could actually become a reality.
Yeah, it is.
But Schneppat doesn't just focus on these big, large-scale things.
Right.
He also talks about the possibility of using QRNGs in everyday devices.
Like smartphones.
Yeah, is that something we can realistically expect to see?
I think it's definitely possible.
Okay.
As technology gets better and things get smaller, we could see QRNGs in everything.
Like in our phones and all sorts of other devices?
Yeah. From mobile devices to those Internet of Things sensors.
It's incredible.
It would mean that every transaction, every bit of data you send is protected by quantum level security.
Wow.
All thanks to this tiny little chip.
Sounds like we're talking about the future of cybersecurity.
I think so, but it's not just security.
What else?
Schneppat thinks that QRNGs could lead to some really groundbreaking changes in other fields like AI and blockchain.
That makes sense. They're already making waves in those areas.
In AI, QRNGs could make machine learning algorithms better.
Okay.
Leading to more powerful AI systems, maybe even ones that are more creative.
Huh, that's interesting.
And in blockchain, QRNGs could make cryptocurrency transactions even safer and more efficient.
Wow, it really seems like we're just beginning to understand what's possible with this technology.
I think that's right.
So Yurgo Schneppat has given us this incredible look into a future where quantum randomness is just built into how we live and work online.
It affects how we communicate, how we do research.
It even changes how we protect our data and play games.
It's a future full of possibilities.
Definitely.
One where this seemingly strange world of quantum mechanics actually makes our lives better in a real way.
From these ultra-secure communication networks to even more powerful and reliable AI.
The potential's pretty amazing.
It really is. This deep dive has been eye-opening for me.
Yeah.
I'm honestly in awe of what the future might hold.
Yeah, it's exciting.
We've only scratched the surface of what QRNGs can do.
That's true.
For anyone who wants to learn more, I highly recommend reading Schneppat's full article.
It's a great place to start.
It is.
If you're interested in learning more about this fascinating field.
It will definitely get you thinking.
Yeah.
Until next time.
Okay.
Keep exploring the quantum realm and don't be afraid to embrace a little randomness.
Good advice.